All right. Hello, everyone. Thank you very much for coming here this morning. I would like to present our work, AI planning and a primary survey with our wonderful collaborators on the screen here. But it's a survey on like AI planning and generalized planning in general. But in this talk, I'm going to focus specifically on generalization in AI planning and learning for planning and so on. I also have some special acknowledgements to Sheila and Tom here for discussions with this work. So let's get started. I'll quickly talk about AI planning. Just keep this interactive. Who here is like kind of familiar with AI planning? Like just put your hand up. Okay, so not everyone here. I'll just quickly give you the main ideas and run through. Firstly, well, AI planning, I refer to it as solving sequential decision-making problems via formal and modeling languages. And most common of these is PDDL, as you've probably heard of somewhere before in this conference or in general. There are many other languages such as PPDDL, RDDL, Golog, so on, with various extensions on top of PDDL. And the main idea of using models is that you can specify the physics of the world. You can also specify preferences and objectives to agents in a formal way. And yeah, so AI planning, like an idea of like the languages we use in AI planning is that we use some first order logic to define states and reusable actions. So more specifically, we can define, a sequential decision-making problem via a domain, which consists of a bunch of predicates, with which you can define states, action schema, which you can define transitions. And next, you have instances, which are like specific tasks that you solve. And these consist of like objects, an initial state, and a goal condition. Pretty much a solution for a planning problem now is just, any policy or sequence of actions that can achieve a goal from your initial state. This is a very kind of informal description of AI planning here. You can make this more explicit. One key takeaway is that, you have this domain and you can reuse this across instances. So common example you might see in literature, maybe in robotics or something, is some pickup action which you define using preconditions and effects. Your pickup action here has like some parameters, your agent, your object, location, and you have some precondition for which you can pick up stuff, and then the effects. So again, yeah, you can use this across problems with different number of objects because this is a first order kind of description. You can also use it across different types of objects and also, different types of low-level action executions. So some pictures here, for example, you have like a delivery robot carrying food around. It's like Uber Eats delivery robot. You have Spot the robot picking up your laundry and dirty clothes on the ground. You can also, have a delivery trucks that can also pick up and put down things. And yeah, so that's, I guess, AI planning in a nutshell. But in this talk specifically for, I guess, the RL audience here, I'm going to talk about how AI planning, can help you define and solve generalization problems. In this talk, I'm just going to quickly, very briefly talk about 3 forms of generalization that we actually cover in AI planning. First of which is generalized planning, so learning to generalize across number of objects, learning for planning, learning to generalize across different goals, and learning planning models, which is, learning to generalize across domains. Again, I'll go through this very briefly. You can look at our paper for more details and slightly more comprehensive survey. So generalized planning, I like to call this kind of model-driven generalization. I'm going to refer to generalized planning as both the methodology and also the problem statement. So the problem statement or the setup now is it's similar to a planning instance. So now we have a domain again, a set of predicates and schema. But instead of having a single instance, we have a set of possibly infinitely many instances. So like a set of instances here. And these instances may have arbitrarily many objects. For example, the I instance may have I objects. For example, the Spot the robot example earlier, you pick up I socks and put them in the laundry basket. And a solution for generalized planning is now a single policy, emphasis on single, that solves every instance in the set I. So a single policy that can solve many different problems. So you can kind of see where generalization comes in now. Some more references. So yeah, again, here's an example. You know, you might have a robot, you want to clean your room, pick up socks, dirty socks in the ground, put them in the laundry basket. And then, you know, you might get a bit lazier because you rely on the robot so much. So gradually, there's more socks that build up over the lifetime of your room. Anyway, that's just an example of, you know, generalization across number of objects. So, you know, question is, okay, how do people synthesize policies? Like, what are the approaches to solve generalized planning problems? So in this few slides I have here, I'm gonna, you know, kind of step through what people try to solve. So when you have like many different instances, you have like many different transitions. For example, on the left here, I don't know if you can see from the text, if these circles represent states, rectangles represent actions. If you have one sock in the bedroom and you pick up that sock, you move to a different state, which is now you're holding that sock and the sock is not in the bedroom. So very simple. On the right here, you know, if you have more socks, there's more like actions you can do. You can pick up the middle sock, you know, sock 2 and hold it. You can pick up sock 1, a different action occurs, pick up sock 3, different action occurs. So what can we do? You know, how do we synthesize policies here? Well, one of the ideas in generalized planning is, you know, abstraction is all you need, like the keyword abstraction. So, you know, we can abstract equivalent objects away. So we can now turn objects into numbers. So instead of saying, okay, we have 3 socks, like 3 unique socks, we have like just 3 socks in general. And then once we pick up any sock, we have 2 socks in the bedroom, and now we're holding 1. If we have 1,000 socks, you pick up 1, you have 999, so on. But here we still have many, you know, different possible instances. And the idea here is, you know, how do we generalize across different objects? Well, we can, you know, abstract even further. We can, instead of, you know, referring to numbers explicitly, we can have just, you know, compare to 0. So you either have socks in the bedroom or you don't. And when you pick up a sock, now this is describing a non-deterministic action. So you can either pick up a sock, there's either still more socks in the bedroom or there isn't. So there's 2 possible effects. And yeah, so we have pretty much collapsed possibly infinitely many instances into one. In words, you know, what generalized planning approaches do is that we learn an abstraction of a set of instances into a single non-deterministic planning instance. And yeah, it's one of the main takeaways of generalized planning. I left a bunch of other details out. This is all again in the literature and in the survey, I think. Okay, so that's the first form of generalization, you know, model-driven generalization across number of objects. Now I'm going to talk more about, you know, learning approaches, data-driven approaches. So why would we want to use these approaches, you know, learning for planning, L4P? I'm going to motivate this with some of the drawbacks of generalized planning approaches. One is that, you know, implicitly, explicitly, these GP approaches assume some certain assumptions on the initial state and goal structures. So learning can help here because, you know, we can learn these, you know, assumptions easily from data. Usually these methods are 0 or 1, so they either work or fail. So when we use like, you know, statistical approaches, we usually allow for some leeway and so on. And 3, like there's no single approach that can solve all possible p-time domains. So in learning, we can, you know, fall back on search. And just quickly, I'd like to mention how, you know, AI planning models can also help with learning. You know, models can help give you very efficiently generated supervised training data, so you don't need to do reinforcement learning. Although you can still do reinforcement learning on top of AI planning. We get some additional relational inductive biases. We have really efficient search engines. And yeah, now I'm just going to quickly go through different methodologies of learning for planning. One of them is policies, so map a function which maps states to actions. And yeah, these are a bunch of different ways people do it. You know, you can learn action scorers, you can learn which actions the best to take in each state. You can learn global value functions, which kind of are like action scorers as well. You know, you can learn or synthesize, you know, policies via code, large language models. There's also very like rich history in like older symbolic methods for learning policies, and they're still very successful today. Yeah. Another thing you can learn is heuristics. So some lessons we draw from deep learning, Rich Sutton's bit of lesson, everything's just scaling from learning and search. Now we have large language models, which is the same idea, train time, test time, compute, again, just learning and search. So one good thing about search is it's complete and sound. It can handle mistakes. And yeah, here's some just more works that, learn from supervision, learn these heuristics from supervision or reinforcement learning. Just running out of time, you can also learn meta knowledge. So you can learn problem transformations to make instances easier to solve. You can learn planet portfolios. Idea here is that, due to no free lunch theorem, there's no single, approach that works well for all planning problems. So we can learn different approaches there. And lastly, so I have technically 0 minutes left. So eating into some Q&A time here. We can learn planning models. So why should we learn planning models? Well, what's the motivation here? So one downside of AI planning is that, we need to hand code all these structural languages for describing the world. So this is quite a burden. Automation here is really nice. We also have other benefits from, I guess, model-based reinforcement learning, improving sample efficiency, learning speed, safety of agents. Again, tying back to the theme of generalization here, we can reuse models across instances with similar dynamics. And yeah, there's three main methodologies again that you can look into the paper again a bit more to see how people do this. One, you learn from abstract state action traces. You try to learn what the action semantics are from analyzing state transitions. More interestingly, you can learn from images so you don't even need abstract state spaces. You can learn from just raw sensory data. This is quite a new field and I guess quite common in general. Another thing is, to learn from directed exploration. You kind of want to explore the environment and try to query the environment to, build on your model better. So you have, I guess, directed search. What action should I execute more to acquire more samples and querying? So trying to, learn from an agent what model is actually doing, and small references here. So yeah, I'm out of time. So this is the summary slide. Just slide this. Okay, but yeah, thank you very much for your attention. Be taking questions now.
Any questions? I have one. So one of the motivation, can you hear me?
Oh, yeah.
So one of the motivation for lifted planning was also about, working with a large number of objects. So I'm wondering, is there some similarities between generalized planning and lifted planning, or they are totally orthogonal, and can there be a lifted planning approach in generalized planning as well?
Right. So yeah, I guess lifted planning, it's kind of similar. You assume a domain and an instance, and you have this first order lifted definition. I guess when people talk about lifted planning, they just talk about approaches that work on the lifted representation. So they're not really talking about generalization. But to kind of answer your question, I think lifted planning approaches it's one form of generalized planning. You can just solve each instance as a lifted planning problem. But I think the ideas in the actual fields are still kind of different. It's one's trying to generalize, one's just solving each instance in a specific kind of representation. Yeah.
Any questions? Okay, let's thank the speaker again.
Thank you.